Mark Nadal, and we are going to build a database in 30 minutes. So sit back, relax, strap in for this rocket ship of a ride into outer space. Mission objective is, well, you wake up one day and your boss is like, our servers are on fire, and our paid customers are very, very angry. And by the way, all your colleagues, they're out for the weekend. So guess what? You're on DevOps duty. The appropriate response would be, no way, I'm not paid enough. But then your boss is like, please. And you're like, dang it, I've always wanted somebody to ask me that. So your inner geek crumbles and you say, okay. Because, being able to rewrite your corporate legacy system from scratch and build something new and fresh is always a good feeling. It's an exciting challenge to architect a brand new system. So how do we architect that system? Well, I'm going to be choosing to build a peer-to-peer ad hoc mesh network to do multi-master replication. Oh, fun buzzwords. Don't worry. It's not actually that complicated because in the next 20 minutes, we'll be building it and breaking down those hard ideas into simple terms. So our own experience with our database, which is GunDB, MIT licensed open source project. So we're getting 20 million cached reads per second based off of this architecture, 20,000 writes second, and 2,000 table inserts end to end in the browser. So what that means by end to end is two browsers that are connected by federated servers are syncing 2,000 table inserts a second through 4 network hops. So a federated system. So performance-wise, if you look at something like Redis, for cached reads, Redis does about 750,000 cached reads per second. All right, so let's dive in. But before we get into the code, I want to first go over each one of the architectural pieces and talk about the concepts behind them. Stepping way back. Well, what is communication? Communication is a way for at least two peers or two people to exchange information. So if I close my eyes and I just speak, I'm exchanging information with you, even if I don't know you are there. Fortunately, with computers, we always wind up having an IP address or something like that we know who we're talking to, but the algorithm and the system we're going to build needs to be able to work even if you have no clue who you're chatting with. But you do at least need more than one peer in the network for you to be exchanging information. In order for that to work, in order for the communication to be robust, we're going to implement an ad hoc mesh network. What is an ad hoc mesh network? It looks kind of like this. Because I don't know who I'm talking to, but I do have a message that needs to get delivered to the other side, we have the peer on the left that wants to send a message to the peer on the right. But because it doesn't know who it's talking to, it winds up emitting data to those peers. Those peers receive it and re-emit the data, okay? But when they re-emit the data back to the original peer as well as another peer that had already received the data, we see those X marks to say, hey, we're going to deduplicate against that message. And this is to prevent broadcast storms. This is to prevent infinite broadcast loops happening in the communication. At the same time, they're also broadcasting to the peer on the right, our intended recipient. And that intended recipient is running through the same ad hoc mesh network algorithm, which is to rebroadcast back out to those middle peers that it happens to be connected with. But again, they already have that message, so they deduplicate against it. But this is a very robust way to give us message delivery in a completely blind communication setting. So once we have communication, in an ad hoc mesh network, what are we going to do with it? Well, we're going to send data back and forth. I've chosen graphs as the data structure for that because graphs allow us to have key value pairs. They allow us to do tables, relational data, document, as well as graphs itself. So what does a graph look like? You can kind of think of it like this. Imagine a regular old document, but add some fun things in. Like one of the children has a relationship back up to the root, or an item is self-referential to itself, or a sibling is connected to another sibling. So that's what graphs are. Now, if we are exchanging data, graphs, amongst many peers that we're communicating with, and those peers might be offline or online or several hops away, it's likely that if two people make an edit, they might be editing the same thing at the same time. So we have concurrency. Concurrency is a huge problem. We've talked about this before in some of the earlier talks. talks, which is how do you deal with cache invalidation? How do you deal with concurrency? So Gun uses a specific CRDT, which is a fancy word. I've done a lot of tech talks on this before, so I'm not going to go over it in details, but just a quick summary. This may not make any sense to people, is if we receive an update below our lower boundary, we just stick it into a historical log. If we receive an update conflicting exactly on that lower boundary itself, we lexically sort the values and choose the larger of the two. That seems really stupid and naive, but that just guarantees we will get eventual consistency across all machines doing that lexical sort. Now, you wouldn't want to do this for all application logic, but the beautiful thing about this is that you can build any other conflict resolution algorithm on top of this one to have more fine-grained control over how that conflict is going to work. If we receive an update that is within the boundary, well, it's legitimate. Okay? That's how most people treat data transfers. They just treat it as being, oh, this is always legitimate data. But the conflict resolution specifies that within the boundary is the legitimacy. And if that happens, we move the lower boundary up to that data point that we just received. Last edge case is if we receive data above the upper boundary, we defer that state on the state machine for the machine to process it when it arrives at that state. Again, that might not make sense, but there's other talks to explain that. Cool, so once we have this, we got data that is syncing and converging in our ad hoc mesh network between peers. We might actually want to read that data out. So we just do a simple key value lookup. A key value, the data visualization is pretty simple. For a circle, I get a box back. For some key, I get some value back. One-to-one mapping. All right, after we have that, I'm actually going to try and implement a storage engine live while we're talking. And I've personally, in my research, I haven't seen anybody use a Radix tree for a storage engine, but to me it's always made sense. So I don't know if this is new, but I thought it made sense, so I went with it. For people who are not familiar with how a Radix tree works, take this example. We can store both Alex, Alexandria, and Andrew in a more compact form because we group the common prefixes together. All right, let's do it. And I think I'm the first speaker that gets to break the fourth wall. Oh my. Okay, jumping into code. This is the simple communication server that we have. It's just a WebSocket server. That WebSocket server is connected here. And then when we receive a peer on the WebSocket server, we're just going to test to see if we have communication with that peer by sending an update every single second. So let's load that up in the browser. Let's spin this up over here. And boost, boost, boost. That's probably too much. Paste. So we expect to see a message every second. Yes. So we have communication established between two peers. Let me boost this up as well. And is that thing showing up over there? I don't know how to get rid of that. Well, I'll just have to deal with it. All right, now that we have communication, let's implement the ad hoc mesh network. So that's up over here. The code here just is another com.js file for communication. So the only changes that we're making, am I able to, no, okay, I don't know what, oh, that's my bad. So the only changes that we made between these two things is that when we receive a message on the peer connection, we check to see if we already have that message, and then if we do, we just return, and that does the deduplication. And elsewise, if we haven't seen the message before, we're going to track that message. And we upgrade this message here to use the envelope specification for over the wire. And all that is just an object with a mandatory property of hash that has the ID. So we're going to track it there. Code down here, going to paste into the browser after I spin this buddy up. Hit refresh. Whoops, not there. You note that as soon as I receive a message, I actually just send it straight back up to the server. So we would expect to get like an infinite loop happening, but nothing gets logged up here. Just as evidence that this is indeed working, I'm going to go back to the code and get rid of that if statement. So now I would expect the server to actually be printing out that data because we're not deduplicating against it. Spin, paste, run, and yes, indeed. So we do not want that, and that's why this is important. All right, so that's the ad hoc mesh network. Sorry. The way that's working is this deduplication code. It's pretty simple. We have a hash table, which is just a JavaScript object that you put IDs inside of it. And every single time that ID is checked or added, we update the timestamp on that thing. So we keep the liveliness of this message constantly up if we keep on getting it again and again and again. And then all of those just have some sort of age or expiry on them. And then at a set timeout, this is only 20 lines of code. We then delete that. So that way we preserve the RAM. So we're not wasting all of our RAM just on tracking these IDs. All right, now let's move over to how the actually having data works. Again, those are the files we have in here. We're finally upgrading to have a index.html. Woohoo. So the index.html is essentially what we copied and pasted before, except for we're going to have the browser, which is a legitimate peer in the network, also doing the deduplication as well. Now we have this new kind of wire spec. We have, of course, the mandatory hash with the ID that we're tracking, but we also have this put command on the wire spec. Let's go back to the slides to just look really quickly at a graph, so that way we can familiarize people who don't have a reference point. So take a regular old JavaScript object of, let's say, Mark, and name Mark Nadal, and then another object of kitty, name Fluffy, and species kitty, because that's a scientific name for a kitty cat, right? That's not actually. And the cat has a slave, Mark. That's me. I'm the slave to the cat, and Mark has a boss, which is the kitty cat. So this is, a JavaScript object, and technically it's a graph, but you guys use this all the time. However, if you try and send this up to another peer, you get this super annoying JSON.stringify, parse error, circular references. Well, actually, we can just get around that by formatting it as this. But think of, when I talk about graphs, as it simply being this type of object. That's it. All right, jumping back in. So we are going to put this graph, and all that we're going to do in this test is to make sure that the server receives that, not that one, that item. Actually, I get to, use the copy file path. And now on the server, I do receive that graph. Woohoo! OK, so now we need to do conflict resolution on the data that we're sending. So we're going to simulate concurrency with this over here. So let's jump back into, the server, there's nothing really different about it other than I added a console.log, and I then iterate over the peers and send that message back down to the peers. So now for testing, simulating conflict resolution, I'm going to have the browser just randomly send 2 updates to simulate conflict. So the first update is similar to what we had before. We have this data, and then this update, I'm just using a set timeout with random time. And then this update, which updates the species property. Right, so the first update, well, it's not actually a first. The concurrent update has species of a kitty, and this other update has a species of Felis sylvestris, which is the actual scientific name for a cat. And if you were to compare this against, let's say, name Mark Nadal with a conflicting update of name Mark, you notice we've added vector states into our update. This is required for the conflict resolution algorithm to work. Because the name has a vector of 2 compared to this name of Mark of a vector of 1, this one will always win out because it is larger. So we should always see in the data after the concurrency has happened that it resolves to Mark Nadal. But what if you have 2 states or vectors that are the same? That's what's going on with species here. Species is a vector state of 2, and species is a vector state of 2 here as well. And this is where we're going to defer to lexical sort and always converge to species Felis sylvestris because it is lexically larger than a kitty. All right, now let's test to see if that works, and I'll show you the code server side in just a second, but let's just, after 2 seconds, oh no! Oh, that's because I didn't switch over to that section of the slide. All right, spinning up the server again. We wind up receiving an update. The first update that we received happened to be the one with Felis sylvestris. The second update we had was a kitty. However, because we are converging on the data using the conflict resolution algorithm, it still stays as Felis sylvestris. Let's do this again to hopefully get the other order, the other concurrent conflict of the data. Refresh. No, we get the same order that time, so refresh. And this time, okay, we got a kitty first, and then we got Felis sylvestris second, but the data is the same as before. And if you note that these 2 updates have actually merged together, which is really, really nice because that just kind of automatically handles a lot of things for you. All right, so jumping back to the server-side code for this, after these check and track functions, all we've added is the wire spec of .put, and we call this function of ham.mix. So what is it doing? It's mixing the incoming graph from the peer with the graph that we have in memory on the server. How that works is, well, here's the conflict resolution algorithm that I explained just a minute ago. Go check out the tech talks. I'm not going to actually go over it, but it is only 25 lines of code. But the mix function is we're iterating over each node in the graph, and then for each key value in each node, we're then grabbing the vector states off of what we have in memory and the incoming update, as well as the data, and we run it through the conflict resolution algorithm. As long as it's not one of these edge cases that we're going to have to handle at some point, I don't handle it here, then it's a legitimate update that is within that boundary function. And then we just go ahead and update our graph directly. And we also calculate the diff on it, which will be useful for us later, but not right now. So that's the only thing that this server is now doing. All right, so jumping into, now that we have data that is synchronizing across the network, we want to query it. We want to get a key value lookup. So let's jump into this code. Again, not much of a change. Let's run the server and just test. I expect, well, I'll show you the code first. It's the same code as before. We're randomly sending the two updates out to simulate concurrency. But then 2 seconds later, I'm making a GET request to the network. And actually, I'm going to say, hey, this is what the wire spec for a GET looks like. It says, get me the key value of FDSA. So let's test that. I expect in the browser, after 2 seconds, to get the data back from the server. Oh, I didn't actually go over. I need to remember that to this piece. Let me restart. It did actually come in, but 1,000, 1,000, precious time that I'm losing here. All right, we now have received this little @ sign is an acknowledgement symbol in the wire spec. We receive a graph that the peer sent me in response, and it indeed has all the data on it. Yes. But to get fun, let's just do one more thing in here. The wire spec allows us to say, hey, we want to select one property off of that node in the graph. So let's rerun this, and I expect to get the same thing back except for just one property on that. 2 seconds later, shlabam, and we have just species. Wonderful. How does that work? Not much of a change here on the server side. All we've done is after we do that ham, it means hypothetical amnesia machine is the conflict resolution algorithm. Don't worry about it. Message is not actually having bacon in your source code. I'm vegetarian, so we've added this thing to the wire spec message.get, and it just says, hey, we get an acknowledgement calling this get function, and if that ack happens to exist, emit this back down to the peers with that acknowledgement. Emit is just a utility wraparound peers.forEach. So get, all it's doing is saying, hey, let's grab the UUID or the ID, or we call it a soul, and see if that ID, that node, happens to be in the graph that we have on the server. If it does, let's just go ahead and ack that back to the browser. But since we also added that extra thing of being able to pluck one item off of the node and only return that, that's what this key property of dot in the wire spec allows us to do. And this is just performing a pluck operation, which is select one item off of it. Again, like 17 lines of code. All right, so we have achieved in 23 minutes a complete in-memory, multi-master replicated database that we are able to save data that converges across an ad hoc mesh network, and we're able to get data back from it. And all of that code was about 200 lines, so not too bad. But now, if we're going to implement the storage engine, this is where it gets a little bit more ugly, because the storage engine itself is 200 lines, and I don't have a ton of time to cover it. So let's first of all just test to see if it works, and then I'll see if I can squeeze out the results. So node.com. Again, on the browser side, all we're doing here is the same thing as before. So nothing's really changed between the two code. So let's hit refresh here. And I get 2 responses here. These responses are actually the acknowledgement from the disk driver saying, hey, it's OK, we actually saved your data. Because we did 2 updates, we got 2 acks back. So we're actually guaranteed your data's on disk, unlike MongoDB. So we actually have data on disk. And then this last thing here is the GET request that we still performed. And we have that one property on it. it doesn't really make any difference. But let's see if that data actually exists on the server, though. All right, we have that raw data file folder, and inside of that, ooh, there's the data on disk. To prove this is actually working, I'm going to go to the browser, turn off the browser from making those changes, get rid of that latency there. And since we are resetting the server does not have it in memory. The browser does not have it in memory. So now we're going to rerun this, which is forcing that we must necessarily be getting the data from disk. Let's roll. And there we already have it. That was lickety-split. And we have the data back, all of it. And it's the converged data that we were expecting. Okay, do we have time to actually explore what it looks like? Well, server side, not much has changed here. Inside of message.put, we are actually saying, hey, change is equal to ham.mix. And that's actually the diff that we got back that I mentioned earlier, because we can take that diff and pass it to this, this wrapper function, store.put, which is a wrapper around the storage engine to say, hey, save this change to disk, and we'll get back error OK. And if we get back error OK, let's emit that back down to the peer so that they have a guarantee that their data was saved to disk. Same thing with message.get, right? If we don't have that message in that data, that node in memory, it'll go into else statement of saying store.get, and we send it back. So what does store.js look like? Well, it's got these two things. It's saying, hey, we need to require Radix, and we need to require Radisk. Radix is just an in-memory JavaScript implementation of a Radix tree. It's about 45 lines of code. I don't have time to actually go over how this works, but it's a pretty well-known data structure, so you can just Google it, and you'll be able to pick up on it and figure out what's happening. Just think of the visualization that I showed you. But that's in memory. Here is the same thing, except for implemented on disk, which was kind of fun. Because this Radix on disk, thus Radisk, pretty clever, right? I also have made it abstracted, so that way it could run on top of like Amazon S3 or a file system. So we actually need to pass it a file system abstraction, which is what this here is. It says, hey, we need put, we need get, and we need list. And that's not doing anything anything interesting other than just literally Node.js's native API of write file, read file, and read directory. So we create a new Radisk by passing it the file system abstraction. And we have the API that you saw earlier, which just really quickly, we iterate over each node in the graph, the change set graph, the diff, and then for each key value on that, we're then going to call the storage engine, which is just a pure key value store, with the UID plus the key to concatenate them together, and we're also going to concatenate the vector states and the value of the data. So, and then the reason why this acknowledgement is counting down is because since the graph will have multiple properties on it, we want to make sure we only acknowledge the browser if all of them have been saved. So that's just what's happening there. So now, and a little bit of time left. Here is the Radisk storage engine. We got some options, but let's jump down to the important part. This is the interface that we were just using, that we get the key. This differentiates between whether we're doing a GET request or a PUT request. So the important part is here, but you're saying like, well, that's not much code for actually putting data to disk. And you're right, all this does right here is batch things. Because disk operations are expensive, so you want to batch as much as you can and then flush to disk. And you can, there's option settings that were mentioned above earlier that you can change the frequency that it flushes to disk. Right now, I think it's set to like 1 millisecond. So after, you want to make sure you're not thrashing the disk, so that we call this thrash function, and it then tries to save the batch that we have to disk. However, if we wind up saving it twice in a row, we want to make sure that we're not concurrently writing to the same file, because Node.js will corrupt it. So all this function here does is checks to see if we are in the process of writing, and then once we're done writing, if we have more, we thrash to disk again, and that just prevents, it just lets our writes be atomic to disk. So the interesting stuff, time check, okay, is this save function. In order for this to work is we have to say, hey, for this in-memory Radix update, okay, iterate over it such that we grab the first key in it, and now we need to check on the file system if there's any file that corresponds to that key. So we go over the file names until we find a file name that is lexically larger than the key in the Radix tree that we're trying to save. We then choose the file right before that as where this key that we're updating belongs. So that is what this find function does. So once we then have found that, we then grab the file before it, right? and then we're going to say, hey, we want to mix these things together, but before we can mix them, we actually have to take that Radix that is actually on disk, read it into memory, parse it into a Radix tree, and that's what we're doing here, which we get now the in-memory representation of that disk file. And now we want to blend the in-memory update with the Radix storage, the file together, and that's what we're happening right here. We iterate over that tree, and then we combine them together, calling this function. And once we've blended them together, we've now merged that file, and we can write to disk. Now, you want to actually perform this for however many keys in your Radix update are remaining until you have a key in your in-memory update that is larger than the file name that you were saving to. And that's what this s.next does, is if we wind up going over that limit of the current file name, we then go to the next file and save the data there and just recursively do what we did before. However, r.write is not as simple as what you would want it to be. r.write also has to check that when it's writing that back to disk, we want to make sure that that file isn't just growing and growing and growing and growing. So we have a limit as we're iterating over now this merged in-memory version that goes back to disk. We want to make sure that as we encode it into a string to put on disk, that that string is not larger than the file limit that we have set in the options. If it is, we're going to perform a fractal split function, which actually isn't that, it sounds fancy, but it's not. All it's saying is approximate the halfway point in this thing that we're trying to save, which is that thing. And then we're going to create two sub-Radix trees. Okay, and then we're going to take, and in order to create those two sub-Radix trees, we have to iterate over that original merged file and slice it in half, which is what this slice function does for those particular limits. Now, we're able to recursively call r.write with these smaller files, with the larger file that just got split in half, with two new file names. And that is how we do Radix storage engine. So that actually gives us O1 lookup time, even if the data grows and grows and grows and grows and grows. Technically, it's O1 because even though you're scanning over the file names, you can actually have the file names in memory represented as a Radix tree itself. So then you're able to do an immediate lookup for which file that you're trying to write to. Which is then O in for the length of the file name, but not O in for the length of all the data you have. So it's O1 with respect to all the data you have. Whew, all right, I want to remind you, we already saw a demo of that working. And again, I can just print out the data here that it is on disk. So in 30 minutes, we have successfully implemented a communication system that uses an ad hoc mesh network with graph data, allowing us to do any type of data, that then converges and synchronizes across those peers regardless of latency or concurrency, that then also allows us to read that data out and flushes it permanently to disk with guaranteed acknowledgement responses in less than 30 minutes, right? So if Elon Musk can build rocket ships that descend from outer space and land on a tiny little platform in the middle of the ocean, surely, engineering software should be easier than building rocket ships that are 40 stories tall, right? So I just want to encourage you, take the most ambitious idea that you have, break it down into simple concepts, understand the architecture, grab a bunch of friends together and build something really awesome, because together we can build incredible software if we think and actually go out and do. So I want to end with this quote from Dr. Seuss. Oh, the thinks that you can think if only you try. Thank you.